Okay, so hello everyone, and thank you for the introduction. So today I would like to present you a platform that we use at ETH Zurich to teach our students how the internet practically works. So let's start with this question. How do we traditionally teach how the internet works? So traditionally we first start with the theory. We explain them what is an IP address, how do the different protocol works. Then we ask them to solve some questions on a sheet of paper, so we can ask them to run an algorithm on a given topology, for instance. And then finally, sometimes the student, they have the chance to play with some real hardware. Few of them because they're expensive, but they can connect them together, configure some protocols, and make sure that the connectivity is working fine. So this is useful, definitely, but not sufficient to understand how the internet practically works. And I think as network operators, you probably know better than me that the internet is more than just configuring some protocols. So what is the internet in practice? So in practice, the internet is network operators, and they are peering agreements. Like I'm sure amongst you there are network operators that meet today at Nanog, and they make peering agreements. And behind these peering agreements, there is a business. And there are also very strong SLAs. So as a network operator, you want to make sure that the connectivity is working at any time. In practice, also, there are thousands of ASCs, and connectivity must be monitored network-wide. So there are a lot of tools that have been designed to help network operators to monitor their network network-wide. So for instance, this is a connectivity matrix, sort of connectivity matrix, which indicates the paths that are used between two different points. And there are a lot of tools like this. I'm sure that amongst you, maybe some of you actually work for companies who develop such kind of visualization tools. But this is something, when you're a student, this is something that you don't really realize when you are just playing with few devices on a small lab. In practice as well, debugging can be very tricky. Very often on the Nanog mailing list, there are people posting trace routes because they don't understand what's going on. So they are asking for some help. And it's very tricky because when there is a problem, you don't know where does the problem come from. Does it come from your own network? Does it come from someone else's network? So really, it's sometimes very tricky. So for those reasons, we have decided at ETH Zurich to use another approach to teach how the internet works in practice. So what we do is we let the students operate their own mini internet, and we let them do this all together like if they were the network operators. So I really want to emphasize the fact that they have to work all together here. So they have to talk, they have to make agreements like if they were network operators. So here, for instance, is a picture of our students working on that project at ETH. And again, you can see they are working together, and they are working towards the same goal, enabling internet-wide connectivity. Okay, so we have been running this platform for 4 years now, and it turns out that the feedback we received is very positive. The students, they say that it allows them to apply the theoretical concepts that they have learned during the lecture. They say that now they are much more confident about many things in the internet. And finally, they generally like the project because it's not like a usual project where they have to implement something in Python, for instance. Here, all of them are involved, and they have to use tools that they are not generally used to use. So they like it very much in general. So this is why today I would like to introduce you this platform, and why we decided to introduce you here at Nanog this platform, because we believe that it can be useful for anyone in a university or in a company willing to teach, to train the next generation of network operators. It can also be useful, for instance, here at Nanog. I saw that there are some tutorials where we teach, for instance, this RPKI infrastructure. Maybe we could use this platform to teach it in a network-wide manner. So the outline of this presentation, first I will explain you how the mini internet that we use mimics the real one. Then I will explain you how we use it to turn students into network operators. Then I will explain you how we help the student, because I think you know better than me that it's not easy to configure a network. So we provide them some help, and I will explain you how we do this. And finally, I will explain you how we implemented the platform such that it provides isolation, it scales, and is flexible. So let's start with the first section, which is about how the mini-internet mimics the real one. So on the right here, you have the highest level topology that we used last year during our project. So each node here in the topology is an IS, and there are 60 ISs in total, and they are divided in 6 regions here in orange. So when we design a topology, we always try to make it such that it exhibits the same property that we also find in the internet. So here, for instance, there are tier 1 ISs in red. In the middle, they are connected in a full mesh fashion. They are stub ISs in gray. They don't have customers. They are transit ISs in blue. Those ones have customers and providers and peers. The ISs, they are connected via peer-to-peer link in green here, or via customer-provider links in orange. Finally, we have some IXPs in gray here that interconnect the different regions together. Now regarding the internal topology that we use here. So we always use the same internal topology in every AS. And to build those internal topologies, we use the same technologies that are used in practice. So this means that they are layer 2 switches, they are IP routers, and they are hosts. Okay, so there is one host that is connected to each router and 2 hosts that are connected to each switch. I will explain you why 2 later here, but this is the internal topology that we use in every AS in the topology. Okay, so now we always try to make some realistic stories around this topology, so that the student, they have to solve real problems. So for instance, the first thing that we do is we give names to our routers. So there is one router at London, another one in Zurich, Roma, Barcelona, and so on. Then we assign some bandwidth to each link. So a link can have a high, medium, or low bandwidth. Then we say that the links that interconnect 2 routers in 2 different continents, they are submarine cables. In the layer 2 network, we also say that there are 2 different types of hosts. There are staff members and students. This, for instance, we use it, for instance, to ask the student to configure some VLANs to separate the 2 types of hosts. Finally, we have some VPN servers as well that are connected to some of the switches, so that students can use it to connect their laptop or their smartphone directly into the mini internet. Okay, so now given this topology, I will explain you how we use it to turn students into network operators. So the first thing that we do is we group students in teams of 3, and then we give to each group 1 transit IS and 1 IP prefix that they have to use to configure the network. And now their goal is to enable internet-wide connectivity. So during the project, we always maintain what we call a connectivity matrix. So a connectivity matrix indicates whether 2 ASs can reach each other. So on the X and the Y axis, you have the different AS numbers, and then one cell indicates whether the 2 corresponding AS number can reach each other. So if the cell is green, it means they can. If it's red, they cannot. So we update this matrix every minute using some ping measurements, and we upload it on a website such that the student, they can look at it in almost real time. So now the first thing that we ask the student to do is to configure intra-domain routing. So first, what they have to do is to configure IP addresses, then they have to configure OSPF, and then after this, we ask them to configure some more advanced policies. For instance, traffic engineering in this case. So for instance, in the layer 2 network, we ask them to configure like custom spanning trees, for instance, or some VLANs, as I said before. In the layer 3 network, we can ask them to do some load balancing. We can also ask them to do some other types of traffic engineering. So for example, on the right here, you have the internal topology that I showed you before. So we typically ask them, for instance, to use the OSPF weights such that the traffic always uses the path with the highest bandwidth. And then on top of this, we can also ask the student to configure additional things such that the traffic from Zurich destined to Roma uses the direct link with the low delay. So here they have to configure static routes on top of OSPF. So they will have to play with all the different tools so that they understand how everything works together. Okay, so at the end of this phase, the diagonal of the matrix should now be green. But if one group fails to actually properly configure intra-domain routing, then the corresponding cell should still be red, in which case we can quickly pinpoint the problem and help this group. So in the second phase of the project, we ask the student to configure inter-domain routing, so to establish the eBGP sessions. So here what we do is we organize a hackathon where all the students, they gather such that they can configure the eBGP sessions together. So one group of students will talk with the neighboring groups, and they will talk and they will decide which IP addresses they want to use to configure the eBGP sessions, and they can also debug and monitor together. So in general, the students, they really like this event. And after this event, the matrix now should be mostly green, mostly because, of course, there are always some groups that misconfigure BGP, in which case some columns or some rows of the matrix will be red. So again, we can easily pinpoint the problem and help them. After this phase, so in the third phase, now we ask them to configure some more advanced routing policies. So for instance, what types of external routing policies we ask them to implement? First, we generally ask them to implement policies such that the traffic follows the money, so the customer-provider business relationships. So here they have to use some local preferences. They have to also implement the exploitation rules. We can also ask them to implement additional policies, like for instance, one provider is preferred over another. So typically what we ask here, just to illustrate it with this simple example on the right, we have the student IS at the bottom. There are two providers, provider 1, provider 2, and there are two routers in the provider 2. So now what we can ask them to do is to implement BGP policies such that the inbound traffic coming from a provider preferably arrives via R2. So here they have to use ISPath prepending, they have to perhaps use the MED attribute and these kind of things. Okay, so at the end of this phase, again, the matrix should be mostly green, but not entirely. If they do not properly configure the policies, then some part of the mini internet will be disconnected. In which case, again, we can help them if they have problems. Okay, so last year, at the end of the project, up to 96% of the ISEs were connected to each other. So here I have a short animation which shows the evolution of the connectivity matrix during the project. So we actually started to record the connectivity matrix after the first phase. So here the diagonal is already mostly green because they have already configured SPF. There are also some other cells that are green because we automatically pre-configure tier 1 and stub ISEs. So this is why there are some green cells in addition to the diagonal. So now I will run the animation, and you will see that some cells become green, and suddenly the matrix become almost fully green because we had the hackathon and the student, they configure eBGP sessions. But you can see that the matrix is never entirely green because again, the student, they always make some mistakes, they solve them, they make other mistakes, and so on. So it's never fully green, but still last year we managed to reach 96% of connectivity overall. Okay, so to conclude this section, I want to emphasize the fact that with that project, I think the student, they learn more than just configuring some protocols. For instance, they realize that operating the internet is a collective effort. They very often have to talk with their neighboring ISEs and to solve problems together with other students. They also realize that the internet is very fragile. So for instance, during the hackathon, we show them a BGP hijack. We show them that a single command can impact the connectivity of an entire IS network-wide. They also realize that very often the internet can be configured more efficiently. They see that in all the routers that they have, very often it's always the same commands that they have to use, the same lines of commands. There are just some differences, like some IP addresses that they need to change, but very often it's the same commands. So they often come up with like Python scripts, for instance, to automate the configuration. So we believe that this is a nice example of to show that this platform can really train them to solve problems that actual network operators face every day. Okay, so you probably know better than me that it's not easy to operate a network in the internet. There are a lot of challenges. And here in particular, we are talking about students, right? So they are really beginners. It's like, for instance, they don't know how to use a router CLI. They don't know how to use BGP route maps. They are used to programming Python, not to use BGP route maps. Sometimes they don't even know what is a virtual device. So we need to help them here. The good news, though, is that there are tools that we can use to help them. And actually, I will show you that those tools are very similar, sometimes identical, to the tool that network operators use in practice. So yeah, as I said, our students, they don't have any a priori knowledge. And also, they have a limited time budget. They only have 4 weeks to do this project. So we assist them. So first, what we do is we organize Q&A sessions every week, where there are teaching assistants that are here to provide help. Also, what we do is we use a dedicated Slack channel where students, they can ask questions. They can ask questions to other students, or they can ask questions to the teaching assistants. So very often, like in the Nanog mailing list, we see students asking some help about the trace route. They don't understand this trace route, for instance. So we always try to reply as soon as we can. And generally, the students, they like this way of communicating so that they are not lost for a too long time. Monitoring and debugging in network is tricky, as I said before. So here, we provide monitoring and debugging tools. And as I said before, actually the monitoring and debugging tools that we provide them are very similar to the one that we use in practice. So for instance, we actually provide them a looking glass so they can see the routing table of every router in the mini internet via a web interface. They can also perform some active measurements, so they can do ping or trace route from any IS to any other IS in the topology. This is very similar to the RIPE Atlas platform, for instance, that network operators use very often to monitor connectivity from external vantage points, for instance. Finally, we have a DNS that so that students they can use domain names instead of IP addresses. So this helps, for instance, to understand better trace route results. Students are not familiar with routers and switches CLI. So here what we do is we provide them a documentation that is tailored for the mini internet. So we know exactly which question we are going to ask them, and we know which command they will have to use. So in that document, we really explain them precisely how to use these commands. So as an example, we know that every year they have to use this BGP nextstop self command, and every year they struggle and they don't understand how to use it. So we clearly explain them precisely how it works in this document, such that they don't lose hours understanding it. Another thing is that the students, they don't progress at the same speed. Some of them are very motivated, and after the first week, they're almost done. Some others, they start to work on the project during the last week. So it's not always easy to evaluate connectivity when some groups are not progressing very well, for instance. So what we do here is we ensure minimal connectivity. How we do this? First, we provide redundancy in the IS level topology. So each transit IS, so the one that we give to the student, they have 2 providers and 2 customers, so that if one provider fails, there is another one that can still bring connectivity. So this already mitigates the problem. But in addition, what we do is we also pre-configure automatically tier 1 and stub ISs, as well as the IXPs. And this is already enough for the students to answer most of the questions. Students must configure many virtual devices. Right? So what we do here is we actually provide them some tools to facilitate the remote access to those virtual devices. So just in a nutshell, how it works, well, they just need to use two commands to access a router CLI, for instance. First, they need to SSH to the server where the mini internet is running, and then they just have to use a script that we have designed for them to access the router CLI. So only two commands are enough here. Okay, so now finally, I will explain you how we implemented this platform such that it provides isolation, it scales, and it's flexible. So to implement this platform, we use Docker containers. So we have a server, and basically for every router, switch, and host, we use a Docker container. So with Docker container, the good news is that they are isolated, so they have their own routing table, so we can easily build a virtual network by connecting those containers with virtual links, and this is what we do here in this case. So, there are 60 ASs, and in every AS there are a lot of router switches, so in the end there are more than 1,600 Docker containers running in our server. The good news is that Docker containers are very lightweight, so I will show later that this is fine for a single server. But something else I want to say here is that we also want to make sure that the student, they can only access the routers and switches and hosts of their group, right? We don't want a student to access a router of another group. So we use we use additional Docker containers that we call SSH proxy container. And then how it works, basically a student first SSH into the SSH proxy container of its group, and then from that proxy container, it can then SSH only to the container running its routers or switches or hosts, okay? So this is how we do this. We also have, as I said before, some VPN servers, so the student, they can use OpenVPN to connect their laptop or their smartphone directly into the mini internet. For the switches and the routers, we use the state-of-the-art software switch. So we use OpenVSwitch for the switches and FR routing for the routers. FR routing actually provides a CLI that is very similar to actual routers. So students, they are really able to configure like real router at the end of the project. Something else that we did is that we want every year to modify the topology, to adapt the topology, for instance, based on the number of students that we have. So we can do this via configuration files. So for example, in 2016, we used this topology on the left, which was inspired from the Internet 2 topology. On the right, in 2018, we use a topology that was inspired from the switch topology. So we did some tests, we did some tests, and it turns out that a single server with 24 cores and 256 gigabytes of memory can handle a mini internet with 60 ASs. 60 ASs is perfectly fine for 100 students, even more. So when the mini internet is idle, we actually observe that it takes like 30% of the CPUs in average, and 58% of the memory of the server. So this is perfectly fine. Then we added some stress. We for instance, did some hyper sessions. We also advertised some BGP routes, like thousands of BGP routes actually, into the mini internet. And well, obviously, the CPU and memory were more used, but still far from overloading the server. So yes, a single server is enough in practice to run a mini internet with 60 ASs. Okay, so we are still actively working on this project. Every year we try to improve it. So for instance, we are currently trying to develop a visualization framework where the student, they can see the status of each link, different OSPF weight, they can run trace routes, see the result via a nice web interface. We hope to actually deploy this visualization framework next year. We also plan to connect the real internet to the mini internet, so we would like to advertise some prefixes that are in the real internet into the mini internet, so that students, for instance, they can stream video inside the mini internet. Okay, so this concludes my talk. So now what if you want to run your own mini internet for your students? Well, first you have to pull from our GitHub page You have to follow the documentation. Then you can define your topologies using configuration files. And finally, you can run it on your server with a single command. Okay, so thank you very much. I am looking forward for your feedback, and I am also looking forward for your questions if you have some. Thank you.
Hi, how are you? I'm Jose from CU Boulder. Quick question. Do you keep any statistics about how much time the students spend while executing these labs, from the best case to the worst case? Mm-hmm. Typically, there's a stress points in the number of credits associated with this training, so trying to figure out how much.
Yeah, so we allocate 4 weeks, and the lecture that we gives 6 credits, European credits. I don't know if you are familiar with this, but the project counts for 15% of the grades. But basically the thing is that when they do this project, they learn quite a lot, and they learn also things that they have to use at the exam, right? So, but the thing is, it's a project that I find it's hard, but we really try to help them. We don't want them to be stuck for too long time just because they don't know how to configure a protocol. That's not the goal of this project. It's not to be lost because they don't know how to use the BGP next stop self command, right? So yes, it's a tough project, but if you help them enough, it's clearly doable. At the end of the project, generally, most of the group, they are done. There are really some groups that are really, really good, and they really make some script, Python script, everything automated, like really, really good. There are some others, of course, that struggle, and they cannot do it, but generally it works really well. Yeah.
Thank you.
Sure.
Rüdiger Volk, Deutsche Telekom. Hello, Thomas. Very impressive. From my work and my focus, I wonder slightly. You were saying, yes, the students learn that if bad things happen, like hijacking, well, okay, there is actually impact. I wonder whether you actually are including any requirements, suggestions for doing actually security stuff there. I certainly appreciate that pushing that in a serious way into the 4 weeks time frame is likely to stretch it over.
Yes. Actually, I've been there yesterday, and I saw all those presentations about RPKI and all that stuff. And I was looking at FR routing, and it seems that it supports RPKI. So I think that we can definitely try to use it in our platform to teach students how to use it in a network-wide manner. Definitely, it's not easy, I guess. It will require even more time for the student. But also what we can do is we can split the project in different parts. Like we can have a routing part first, and then a security part afterwards, and so on. So clearly, it's as I said, every year we try to improve it, and this is clearly something that we would like to think about. I mean, I'm not telling you that we will do it, but we will think about it definitely. And yes, but you're completely right. So yeah.
Hi, Flavio here. So first of all, thank you, because this is pretty incredible in terms of teaching and tool. One thing that I wanted to is just a small clarification. So you said that you do this with, is it like an intro to networks course? Like you said that you have a priori knowledge?
Yeah, so it's the first computer networks course that our students have. So it's like third year, and sometimes there are also some master students as well. But when they start the lecture, they don't know what is OSPF, BGP, they don't know anything about this. And I mean, when they start the project, sometimes there are students, they don't know what is a subnet. So we really have to explain them. So there are TAs to tell them, okay, you used to use this /24, you used to configure this IP address into this host with this default gateway. So it really starts with the basic things. But at the end, they manage to configure very often everything at the end. So,
yeah.
But again, it takes time to explain them. But
yeah, that's really cool. And second, it's kind of maybe a suggestion / recommendation. Yeah. This is something that definitely could be used in this hackathons. You know, we have the hackathons always before NANOG, and maybe you could use it to show people how our PKI is implemented. I don't know, maybe more advanced things could be approached, but it's really cool.
Yeah, so this platform have been designed for teaching, but clearly it can also be used for other things, like maybe for your research project, although it has not been designed for this, but could be that it can be used for this, for tutorials or whatever you want, right? That's for sure. Yeah. Okay, thank you very much.